Well, I promised you a balancing act. So, today's the day. I think you'll find balancing equations easier than this.
During this lesson, you will use the law of conservation of mass and provide standard rules for writing and balancing equations, as well as write and balance equations originally stated in words.
Chemical equations are used to express what takes place during a chemical reaction. The reactant or reactants in a reaction are placed on the left side of a chemical equation. The product or products are placed on the right-hand side. The arrow between the reactants and products is read as yields. The small numbers to the lower right of the element symbols are called subscripts and indicate the number of atoms of an element present in a molecule. Whole numbers placed in front of the symbols for reactants and products in chemical equations are called coefficients. Coefficients indicate the relative proportions of reactants and products.
Coefficients, reactants, products. Equations involve some complex vocabulary, don't they? So today, we'll start our lesson by making sure you understand the terms you'll be using as you learn about equations. Let's see what Mr. Webster has in here.
A chemical equation is a shorthand way of reporting the details of a chemical reaction. Reactants are the starting substances in the chemical reaction and are placed on the left side of the equation. Products are the substances formed during a chemical reaction and are placed on the right side of the equation. The arrow between the reactants and products is read as yields. The large numbers in front of some of the formulas in a chemical equation are called coefficients. These numbers are used to balance the equation and represent the number of molecules, formula units, or atoms of the substance. We'll talk more about that later, but for now, just remember that like subscripts, a coefficient of 1 is understood, but not written. It's also important to remember that subscripts can never be changed in order to balance a chemical equation. When balancing equations, the only numbers that can be changed are coefficients.
So, reactants are on the left, products are on the right, and coefficients are used to balance equations. I've learned how to balance this meter stick, but what exactly is meant when we say we're to balance an equation?
During chemical reactions, matter is not created or destroyed. The mass of the reactants is equal to the mass of the products. This relationship was first realized by the French chemist Antoine Lavoisier in the late 1700s. Just as in a mathematical equation, the two sides of the equation must be equal or balanced. Chemical equations are balanced by changing coefficients.
We learned about the law of conservation of mass, also called the law of conservation of matter, in Unit 2, when we studied chemical and physical changes. That was a while back, so let's quickly review. After all, this law is why we balance equations in the first place. When a chemical change occurs, substances with new and different properties are formed, but new and different matter is not formed. The matter is only changed to have different properties. This concept is explained by the law of conservation of mass, which says that mass is not created or destroyed in a chemical reaction. This means that the mass of the substances before the reaction will be equal to the mass of the substances after the reaction, even if the substances are different. Remember the seltzer tablet in the flask? Let's take a closer look at what was going on there.
The mass before the reaction was 174.16 grams.
You can see that the seltzer tablet is in the balloon, but it has not yet reacted with the water. You will remember that the reaction produces a gas. We need the balloon in order to capture the new substance that is produced. Let's look at the mass after the reaction. You can tell that the reaction has taken place because the balloon is full of gas. The mass after the reaction was 174.16 grams. They are the same. If we take the mass without the balloon, you see that the mass is 170.68 grams. It appears that some matter was destroyed, but in reality, it was turned into a gas. If the gas is not captured, its mass is not accounted for. Let's put the law of conservation of mass into your notes. It says that mass is not created or destroyed in a chemical reaction. Throughout the course, we will need to remember this simple experiment that demonstrates this law.
Hey, that guy knows what he's talking about.
And we have to talk about balancing equations because we must abide by the law of conservation of mass when we write a chemical equation. In other words, the total mass of all of the reactants must equal the total mass of all of the products. Another way to look at this is to realize that the number of atoms of any particular element must stay the same on both the reactant and product sides of the equation. Atoms are rearranged during a chemical reaction to form new substances, but they are never created or destroyed. For example, the mass of my delicious world-famous chocolate chip cookies is the same as the mass of all the ingredients I used to make the cookies. The ingredients have changed, a chemical change in fact, so the products are different than the reactants. But the mass of the ingredients I started with equals the mass of the cookies I wind up with after baking. This is the case with all chemical reactions, except maybe for the taste. So, while I reduce the mass of these cookies, let's look at another equation example together.
When zinc reacts with hydrochloric acid, it forms zinc chloride and hydrogen gas. Are atoms conserved in this reaction? Look closely. We see one atom of zinc on each side, so zinc is balanced. But the chlorine and hydrogen don't balance. The reaction shows one atom of hydrogen and one atom of chlorine as reactants, but two atoms of hydrogen and two atoms of chlorine as products. Now it's time for those coefficients we learned about. If we place a coefficient of 2 in front of the hydrochloric acid, the equation will be correctly written and mass will be conserved. Just as in math, the coefficient in front of hydrochloric acid multiplies both the number of hydrogen atoms and the number of chlorine atoms in the chemical formula for hydrochloric acid by 2. Since there are no subscripts, we know that the formula represents one atom of hydrogen and one atom of chlorine. So placing a coefficient of 2 in front of HCl will balance the equation by giving us 2 hydrogen atoms on both the reactant and product sides of the equation and 2 chlorine atoms on both the reactant and product sides of the equation. Zn plus 2HCl yields ZnCl2 plus H2 is a correctly balanced equation following the law of conservation of mass. The mass of the reactants we started with is equal to the mass of the products we wound up with. Look at the unbalanced equation for the reaction between hydrogen and oxygen that produces water. 2 hydrogen atoms are on the left and on the right side of the equation. However, it's clear that there are too few oxygen atoms on the right. It certainly is tempting to simply add a subscript of 2 in the formula for water in order to balance the equation. But remember our rules. Once a correct formula is written, the subscript in the chemical formula can never be changed. Adding a subscript of 2 to the oxygen on the right side of the equation means that the compound isn't water at all, but is hydrogen peroxide.
Since adding a subscript of 2 to the oxygen on the right side of the equation isn't allowed, just how would we balance the equation? Look for just a few moments and see if you can figure it out. You can't change a subscript to balance an equation. Here's a hint that will help you remember this. Draw a box around each formula in the equation before you begin to balance the equation. You can't change anything in the box. That's a great reminder to you that a formula can't be changed once it's written. If you place a 2 in front of hydrogen on the left side of the equation and a 2 in front of water on the right side of the equation, you are correct. According to this equation, there are 4 atoms of hydrogen on each side of the equation and 2 atoms of oxygen on each side of the equation. The law of conservation of mass has been followed and the equation is balanced. 2H2 plus O2 yields 2H2O. Some equations are more difficult to balance than others. If an equation appears to be complicated to balance, start by imagining a coefficient of 1 in front of the compound that contains the largest number of atoms. This often makes balancing a more complicated equation fall into place. Don't forget that 1s are understood, but not written. However, some students find it helpful to write in the 1 as they work the problem, and then erase it when they are finished.
Look at the equation representing the burning of propane. C3H8 plus O2 yields CO2 plus H2O. A quick check on the numbers of atoms of carbon, hydrogen, and oxygen on both sides of the equation shows that the law of conservation of mass hasn't been followed. When equations are more difficult to balance, writing the elements and how many atoms of each are present beneath the reactant and product sides of the equation is often helpful. This is called an element inventory. There are 3 carbon atoms on the reactant side, but only 1 carbon atom on the product side. 8 hydrogen atoms are on the reactant side, but only 2 hydrogen atoms are on the product side. And finally, there are 2 oxygen atoms on the reactant side, but 3 oxygen atoms on the product side. Clearly, the equation isn't balanced. Our element inventory helps you see that. But before you do anything else, take a minute and draw boxes around each formula. Lots of students want to skip this step, but as a beginning chemistry student, it will help keep you from making a careless mistake. Your local teacher will pause the tape now to give you time to balance the equation on your own, and then we'll check your work. Good luck. Local teachers, please pause the tape now.
Were you able to balance the equation? If so, that's great. You're getting the hang of this balancing act. If not, don't worry. You'll have the hang of it soon. By now, you're probably realizing that much of balancing equations is trial and error. It's nice to know that it does get easier with experience. There are some guidelines to make balancing an equation easier, however. Let's get these guidelines into your notes.
Start by making an element inventory. When you first start balancing equations, it's simply too hard to try to keep track of all those numbers in your head. Draw boxes around each formula in the equation. This simply reminds you not to change subscripts in order to balance an equation. Begin with 1 molecule or formula unit of the substance containing the most atoms. Balance polyatomic ions that appear on both sides of the equation as a single unit. Balance hydrogen and oxygen atoms last.
Let's look closer at that hint about polyatomic ions being balanced as a single unit. Maybe you should see an example.
Cu plus AgNO3 yields CuNO3 2 plus Ag. Do you see the polyatomic ion that appears on both sides of the equation? The nitrate ion, NO3, is on both the reactant and product sides of the equation, so we can balance this polyatomic ion as a single unit. To balance the equation, begin with an element inventory. There is one copper atom on each side, one silver atom on each side. But the nitrate ions aren't balanced. There's only one nitrate ion on the reactant side, but two nitrate ions on the product side. Remember that because the nitrate ion appears on both sides of the equation, we can balance it as a single unit. After drawing boxes around each formula, placing a 2 in front of silver nitrate will solve the problem of only having one nitrate ion on the reactant side. Multiplying by 2 will give us 2 silver atoms and 2 nitrate ions on the reactant side of the equation. The nitrate ions are balanced. The problem is, silver isn't balanced now. We can solve that easily, though, if we place a coefficient of 2 in front of silver on the product side. Look closely now at the balanced equation. There is one copper atom on each side of the equation, 2 silver atoms on each side of the equation, and 2 nitrate ions on each side of the equation. Voila! The equation is balanced.
In the example you just saw, the polyatomic nitrate ion was balanced as a single unit. This is always best when the polyatomic ion appears as both a reactant and a product. But sometimes a polyatomic ion doesn't appear on both the reactant and product side. So in that case, you obviously can't balance it as a single unit. Here's an example.
Potassium nitrate decomposes into potassium nitrite and oxygen. Notice that the polyatomic ions on either side of the equation aren't the same. The nitrate ion, NO3, is on the reactant side of the equation, but the polyatomic nitrite ion, NO2, is on the product side of the equation. Because of this, the polyatomic ions can't be balanced as a single unit. For a little more practice at balancing equations, take a few seconds and see if you can balance this equation. Let's examine the balanced equation. A coefficient of 2 in front of potassium nitrate gives you 2 potassium atoms, 2 nitrogen atoms, and 6 oxygen atoms on the reactant side of the equation. A coefficient of 2 in front of potassium nitrite gives you 2 potassium atoms, 2 nitrogen atoms, and 4 plus 2 equals 6 oxygen atoms on the product side. The equation is balanced. Once again, the law of conservation of mass has been satisfied. The number of atoms of each element is the same on either side of the equation.
Now it's your turn to practice. Your local teacher is going to turn off the tape so you can spend some time becoming more comfortable with our balancing act. Good luck.
Local teachers, please turn off the tape now.
How did it go? Are you comfortable balancing equations? I certainly hope so, because we still need to learn a little more about equations. Now, you're going to learn to take a word equation, write it using chemical formulas and symbols, and then balance it so that it follows the law of conservation of mass. Writing chemical equations from word descriptions is really very easy, now that you've learned how to write chemical formulas from names. Here's an example. Write the chemical equation for the reaction between hydrogen and oxygen to produce water. Most students know that H is the symbol for hydrogen and O is the symbol for oxygen. You also probably know that H2O is the formula for water. So, H plus O yields H2O seems reasonable for the chemical equation to represent this reaction, doesn't it? Well, you're on the right track, but there is a catch. Let's get this in your notes.
7 elements exist primarily as diatomic molecules in the elemental state. That means that in an equation, these elements aren't simply represented by a symbol. Instead, they are represented by their symbol with a subscript of 2. The prefix di means 2, so diatomic means 2 atoms. These 7 elements are nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. An easy way to remember these 7 diatomic elements is this. There are 7 elements that exist as diatomic molecules in the elemental state. So starting on the periodic table with nitrogen, which has an atomic number of 7, we'll highlight nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. You'll notice that the number 7 appears as a result of your highlights. Then highlight hydrogen to conclude your list of 7 elements that exist as diatomic molecules rather than as single atoms in the elemental state. What an easy pattern! There are 7 elements that exist as diatomic elemental molecules, and if you start with element number 7, you'll create a 7 on the periodic table. Just don't forget to pick up hydrogen.
Now, back to our equation. The problem, then, with how our equation was written earlier is that hydrogen and oxygen exist as diatomic molecules. So, instead of writing H plus O yields H2O, the correct equation would be H2 plus O2 yields H2O. But is this equation really correct?
No way! According to the law of conservation of mass, matter can neither be created nor destroyed in a chemical reaction. Consequently, the number of atoms of an element on the reactant side of a chemical equation must equal the number of atoms of the element on the product side of the equation. It's really very elementary.
Thanks for the reminder. Now, let's see if you've been paying attention. We balanced the same equation earlier today, so it should be a snap for you to show me again the correctly written equation. Can you? Our students have been paying attention. Look at all of these whiteboards with the correctly balanced equation. Let's give them a hand. Diatomic elements are a new twist to writing a chemical equation from a word description. But the pattern these 7 elements create on the periodic chart will help you remember them. We'll practice writing another equation from its word description, and then your local teacher will have lots more examples for you to work through.
Take a few seconds to write the chemical equation for the following word description. Carbon disulfide reacts with oxygen to produce carbon dioxide and sulfur dioxide. Remember all you've learned about correctly written formulas and balanced equations. Your local teacher will pause the tape now. We'll check your work after you've had time to correctly write the chemical equation using symbols and formulas. Don't forget that an equation isn't correctly written unless it's balanced.
Local teachers, please pause the tape now. First of all, let's look at the chemical formulas for the compounds represented in the equation. Carbon disulfide, carbon dioxide, and sulfur dioxide are all molecular compounds. The prefix di means 2, so writing these formulas is easy. Carbon disulfide is CS2, carbon dioxide is CO2, and sulfur dioxide is written SO2. The only substance left is oxygen, which is one of the 7 diatomic elements, so it is written O2. Now, we add in the appropriate plus symbols and the yield zero, and this gives us the chemical equation CS2 plus O2 yields CO2 plus SO2.
As previously mentioned, according to the law of conservation of mass, matter can neither be created nor destroyed in a chemical reaction. Consequently, the number of atoms of an element on the reactant side of the equation must equal the number of atoms of the element on the product side of the equation. I'm afraid that isn't the case with this equation.
Our student is exactly right. We still need to balance the equation. Let's go to our classroom and see how the students are doing. How did you do? It looks as though our students have this balancing act down. CS2 plus 3O2 yields CO2 plus 2 SO2. 1 carbon atom on each side, 2 sulfur atoms on each side, and 6 oxygen atoms on each side. You've got it. Balancing isn't so hard after all, is it? Your local teacher will have lots of practice for you so that you will become a real pro. But right now, it's time for the chemistry quiz.
Let's begin our quiz with cumulative review question number 1. Who is credited with the first atomic theory that is based on experimental evidence? A. Democritus, B. Aristotle, C. Dalton, D. Rutherford. For cumulative review question number 2. In an ionic compound, the chemical formula represents A. 1 molecule of the compound, B. 1 formula unit of the compound, C. the simplest ratio of positive to negative ions in the compound, D. both B and C. Let's get started with a review of today's lesson. Question number 1. The starting substances in a chemical reaction are called the A. products, B. yield, C. reactants, D. coefficients. Question number 2 is true or false. An equation is said to be balanced if it follows the law of conservation of mass. A. True, B. False. Question number 3. Choose the coefficients which in order would correctly balance the following equation. HgO yields Hg plus O2. A. 1, 1, 1. B. 2, 1, 1. C. 2, 2, 1. D. 2, 2, 2. Number 4. When balancing a chemical equation, one is allowed to adjust the A. formulas of the reactants, B. formulas of the products, C. coefficients, D. both A and B. Number 5 is true or false. In a chemical equation, the arrow is read as yields. A. True. B. False.
Well, my full stomach tells me that the law of conservation of mass is true. The chocolate chip cookie matter has neither been created nor destroyed in the chemical reaction associated with my eating most of these things. But in the interest of scientific investigation, I better eat a few more just to make sure. Until next time.